All right, welcome back. Sorry we had some technical difficulties on the last part of the lecture. I had to stop in the middle of the chapter and come back to it. So let's kind of pick up where we left off. We were just talking about piping systems and how they withstand pressures over 1,000 pounds per square inch and temperatures of a negative 200 to a plus 1,200 degrees. And with alloying and materials, we can get higher temperatures and higher pressure than that for sure. So, back to the chapter. We are going to start again at chapters 22, or page 22, chapter 2, because I'm not really sure where the SD card ran out on the last lecture, so we might be doing a little double lecture here, okay? I believe it was right around talking about the pipeline, so forth. You know, this is a typical pipeline setup. It's here. If you notice, you can see one walled seam here. You don't see the seam matching up. When we get in the shop and we're doing weld testing, I'll have you match the seams. But in real life, you want to make sure that your seams are on opposite ends. Either some companies require at least 90 degrees, some of them require 180 degrees off from each other, so forth. To make sure that if there's a weak link in the pipe, it's not all going to be in the same spot, okay? Typically, on most pipeline jobs, you'll have production this way versus a lot of tie-ins. Production, you'll have one person that'll do the root pass, so the first welder will be ahead, and he'll do the first root pass. He'll move on, or you'll stop, you'll leave the keyhole open, the inspector will come, you'll check your keyhole, you'll be able to look through the pipe, check everything out. A lot of times you can be sitting there watching them weld it while they're doing so. Make sure it's good. There's no repairs that need done on visual inspection at that point. That welder will move on to the next pipe joint. Second welder come through, do a hot pass, check it. Sometimes they'll even do the fill passes. And then usually you have somebody or two people that'll come back and they'll fill the whole top end at one time. A lot of times on a pipeline you'll have welders doing, if a pipe is this way, you'll have two welders going from top to bottom. In the field they refer to it as brother-in-law. What it does is it keeps heat and distortion. It just speeds up the process. It minimizes the amount of heat input that you're putting into it for a long period of time. You can weld it, be done. Two people start on one side or on one pipe joint, and they can finish it up a lot faster. Okay. Let's see where we're at. Talk about railroad equipment. Excuse me. Welding is the principal method of joining materials used by the railroad industry. I'm reading out of the book, sorry. Page 22, chapter 2, right-hand column under railroad equipment. Welding is the principal method of joining materials used by the railroad industry. The railroads first made use of this process as a maintenance tool and has been extended to the building of all rolling stock. It's also used extensively in the construction and the repair of equipment on the right-of-way. Railroad units fabricated by welding include streamlined diesel and electric locomotives, passenger cars, subways, freight cars, tank cars, refrigerator cars, and many other special types. We'll skip down to the next paragraph. It says, weight's an important consideration in the design of freight cars. In an entire train load, a freight engine may be called upon to haul a string of up to 100 freight cars, whose dead weight alone amounts to 2,400 to 3,400 tons. Welding and alloy steel construction reduced the weight of 50-ton box cars from a lightweight empty of 48,000 to 36,000 pounds, a reduction of approximately 25%. These cars are also able to carry a 25% greater load than their former 50-ton capacity. That's important, that's efficiency, okay? So what he's doing here, we start talking about several rail cars in various stages of completion, size of this fabrication area, air carbon arc gouging is being used. That's what he's doing here. You'll learn about that more through oxy-fuel welding and so forth. Highly effective tool. You can cut through 2-inch thick plate in a matter of a minute to 2 minutes, okay? And you don't have to wait for the heat to heat it up like you would with oxyacetylene torch or even a plasma with a big large machine. Talked about reduction of weight and greater payloads. Here's a good one right here. Freight cars have life of 20 to 40 years with very little maintenance. A lot of times, the majority of the maintenance, as long as they're not beat up too bad, is on the rolling gear and the wheel sets. The suspension within those as well. That's the majority of the maintenance. Good example, hopper cars redesigned, saving weight. Hopper cars now made of aluminum with steel for the underframe, 2 to 4 components, up to 4,000 feet of weld. It's a ton of weld, almost a mile. Okay, we're going to move on. Shipbuilding. We're going to turn to page 25, chapter 2. Left-hand column, halfway down the page, shipbuilding. Okay. Naval limitation treaties of the 1920s and 30s were the impetus behind the research program that led to a new conception of welding and ship construction. Under these treaties, the various nations agreed to limit not only the number of capital vessels built, but also their weight. The Navy's reaction, therefore, was to build the most highly effective ships possible by any method within the limitations of the treaties. Okay? Naval limitation treaties of the 20s and the 30s. I'm going to keep reading from the book. Next paragraph down, that welded ships can take it is borne out by the story of the USS Kearney, which limped into port on October 18, 1941. This fighting ship blasted amidships by a torpedo came home under its own power, putting the stamp of approval on a type of construction in which our Navy had been a leader for years. It was highly improbable that any other than a welded type of ship could have reached home, and it was impossible that any other could have rejoined its command, as did the Kearney a few months later. All right, right-hand column, halfway down. The standard specifications for Navy welding work, which cover all welding done for the Bureau of Ships, are concerned with a variety of structures such as watertight and oil-tight longitudinals, bulkheads, tanks, turret assemblies, rudder crossheads, pressure vessels, and pipelines. Air, steam, oil, and water lines in various systems are all of homogeneous welded construction. Okay, so let's read through the PowerPoint. Ships must be light, highly maneuverable, but have defensive armor, plate, gunpowder, and strength. Aircraft carriers, combat vessels, destroyers, cruisers, and nuclear submarines. Welding was done for the Bureau of Ships, concerned with a variety of structures. Talked about longitudinals, bulkheads, tanks, turrets, rudders, pressure vessels, and pipelines. You know, when the Navy builds something, it's going to be out there at sea. You want to talk about the quality control that goes within it as well. They're doing a lot of, number one, the easiest and best non-destructive testing method is visual inspection. If you know what you're looking for and you're trained to know what you look for, visually inspecting it is very important to begin with. You can catch most mistakes at that point. And then depending on what application you need, you might be looking at doing mag particle testing to see if there's any surface issues or slightly subsurface. Liquid penetrant, dye penetrant, to be able to check any holes there. And then it may go into an x-ray or an ultrasound situation. It's where you're checking the interior or the volumetric weld within the entire weld to see the interior surfaces as well, subsurface, not just on the surface. Immense size and jobs and materials range from half to several inches thick, and units weighing up to 250 tons each. A welded rudder of the USS Lexington weighed 129 tons and was 12.5 foot thick. That's unbelievable. That's, you know, So that's 144 inches is 12 foot plus 6 inches, so we're at 150 inches thick. That's pretty amazing. Talked about the welded ship uses, less or approximately 18% less steel than one that is riveted. Let's look at the bottom here. Made from lightweight aluminum, this fairing is fabricated by pulsed gas metal arc welding. We'll get a chance to, we have a pulsed gas machine in there. At the time I'm making these videos, we should be getting our pulsed aluminum MIG guns as well. Before we just had a straight push-pull gun. Both highly effective ways, but we're seeing a lot more pulsed aluminum welding in the field now. I want to read from the book, okay? So page 25, right-hand column, bottom paragraph, it's only the last two sentences. It said, it's now possible to construct submarine hulls with a seam efficiency of 100%, as against the 70% efficiency of riveted hulls. Caulking is unnecessary because the hull is permanently leak-proof. Hull production time is reduced by approximately 25%. The total weight of the hull is reduced by about 15% because of the use of butt joints and groove welded plate. Smooth lines of the welded plate make hulls more streamlined and therefore faster and more maneuverable. Okay, now I want you to jump down 2 paragraphs. The paragraph starts out with ships differ widely. Okay. All right. So ships differ widely. Instead of just a Navy ship, this is a ferry, passenger boat made of lightweight aluminum. Different applications. Same thing with everything in the world of how we use it and how we're going to attack or approach fabricating it as well. Okay. So get back to the book where we found the paragraph, page 26, 2/3 of the way down, left column, starts out, ships differ widely in type and conditions of service. They range from river barges to large cargo and passenger vessels. The adoption of the construction methods used in building ocean-going Liberty ships during World War I has reduced construction time from keel laying to launch by more than 20%. Prefabrication, pre-assembly, and welding are the reasons for the dramatic reduction in building time. Parts and substructures are shaped in advance. Sorry, I'm looking, there's a story in here about some flaws within the Liberty ship that they had to change. I want to make sure that I find the correct info before I start discussing it. And I can't find the info, so we'll refer to it another time. Let's go down to structural steel construction. Okay. Welding process is applied, hydroelectric units, power generation units, bridges, commercial, private buildings. You know, so just in this chapter alone, we have seen such a wide variety of uses for welding and fabrication within the United States. We've looked at, it showed big pressure vessels, it showed pipelines, we looked at ornamental iron. Now we're looking at hydroelectric units, power generation units, bridges, so forth. You know, even the wind-powered turbines have metal welding fabrication involved, and so forth. Where they're definitely a highly effective way to join two pieces of material with longevity. All right, from the book, page 26, right-hand column, underneath structural steel construction towards the bottom. The welding process has been applied to the construction of hydroelectric units, power generation units, the construction, bridges, commercial buildings, and private dwellings, The construction of such superpowered projects as the Bonneville, Grand Coulee, Hoover Dam, and the Tennessee Valley Authority projects called for entirely new methods of construction for water turbine parts and water power machinery. Welded construction is first used extensively for the 74,000 horsepower hydraulic turbines in the Bonneville project on the Columbia River near Portland, Oregon. So right there where we're at, I mean, this is one of the first engineering marvels of of modern hydroelectric power was the Bonneville Dam. Pretty impressive piece of machinery. It is machinery, even though we don't think so. When you drive by and you hardly see anything there. However, there's a lot of work that goes into a lot of engineering. Let's continue reading. The units alone of this power project involved 80,000 feet of gas cutting, 118,000 linear feet of welding, 286,000 pounds of electrodes, and 6,450,000 pounds of rolled plate steel. The Bonneville project demonstrated that the following advantages were realized by the use of welded members. Let's see if we got a... doesn't talk about it. All right, let's go back. Welded members. Let's look at the bulleted pointed items underneath the paragraph we just finished, page 27, left-hand column. I want you to look over all those bulleted items. I'm not going to read them all. It's a good, just a good read. It's amazing the amount of material and work that goes into what we take for granted sometimes because we don't always see it. Okay, so let's go into bridges. Bridges, welded construction reduces weight up to 20% versus riveting. Reduces cost of construction. Rivet construction is 5 times higher. Increase in strength. Welded butt joints the best. It's a solid weld instead of having 2 overlapping pieces where they had to be fish plated. So now what we can do, give you an idea just so some of the basic general understanding. So now we can let's take a side profile. So we're looking at a bridge. We've got the main deck, so forth, support columns, all that, okay? But imagine this is one thick plate. Before, when they wanted to join this, you would see a lot of rivets. So let's look at it from a side profile, material thickness, okay? Doesn't matter how thick it is. Now what we're able to do is we're able to weld this in its entirety. So say this is 2-inch thick material to where the weld is 2 inches thick. It's now just one solid piece of plate. Before, what they had to do, say this was one piece of material, or sorry, 2 pieces of material, was they had to come in and they had to put a fish plate, common terms for it, behind there to be able to help join it. And the rivet head would be here. So just kind of a quick general idea. It's a lot faster, a lot quicker. To just be able to prep that and weld that together will also a lot less weight. If this was 2 inches thick, this may have to be 2 inches thick, also another 500 pounds per welded joint. Versus this, you're talking maybe an extra 8 pounds worth of weld. So we talk about weight reduction, huge benefit. However, you don't just weld it with any welding rod. This has to be able to flex and bend while cars are driving on it, along with seismic activity and everything else. So there's a specific procedure that they're going to have to follow to make sure that there's enough ductility and percent elongation within the welded filler metal that you're using to weld this up. Okay? All right. Just give you a general kind of overview of how traditionally rivets were installed on bridges. Okay. Reduction in stress, rivets as well, increase in strength. talked about this. Sorry. Major method of making joints and structures. We're into commercial buildings now. Okay, so let's go to page 27, right-hand column, 3/4 of the way down. Industrial and commercial buildings. All types of buildings are welded during construction. Welding has become a major method of making joints and structures. The fact that there were no holes needed for rivets is an advantage in the design of trusses and plate girders. So here again, arc welded rigid frames replace conventional truss or sawtooth framing. So if we're looking at this, we don't see our normal truss like we see in a barn going across with our webbing and our support beams. Now we're able to bring it together. It gets a lot more height, a lot more space, so forth. A lot less weight as well. Also, it just says here, note the absence of support columns. Instead, we're able to create a large structure, wide open structure, especially important for large fabrication buildings, arenas, so forth. If we had beams going down here in the center every 10 feet on center, it'd be hard to have a car race or a bike race or a rodeo or something like that within the arena if all those support members are in the way. All right, speeds excavation by use of digging equipment with abrasion resistant teeth. We'll get into that later. Let's look at the book here. Don't have anything major that come out of it, so feel free to read through this section. Prefabricated housing. Metal houses are definitely on the rise. You can do a very thin material and it can come out with the same amount of strength that a 2x4 was designed with as well. They can be pre-built in panels, put together at the site with about a third of the production time to do so to build a traditional stick-framed helm. Welding replaced riveting 75 years ago. Here's a good example. Riveted construction versus all welded construction. Not only do you have to roll the plate, so forth, and still preform it and shape it, but you would have had to have drilled all the holes, plus made all the rivets, heated them up, pounded them in, set them, everything else. Now you just roll the material, weld it all together, done. Okay? It also eliminated leakage and corrosion around the rivets. A lot less problems, a lot less maintenance. Okay, tank and pressure vessel construction, page 29, chapter 2, left-hand column, bottom sentence, or bottom paragraph. It starts out, welding replaced riveting in the fabrication of pressure vessels approximately 65 years ago. Performance of the pressure vessel through the elimination of two common areas of service failure in riveted vessels, leakage and corrosion around rivets. So, two big pointers. Okay? Leakage and corrosion. Skip down to right above the picture of the riveted vessel. There's two bolded points. I want you to highlight those. Elimination of thickness. Limit of about 2 3/4 inches for successful riveting. So forth.